ear. And we went through the little, with our little magic school bus, we went through the ear, we went to the tympanic membrane, we shook some ossicles, and then we got to our inner ear where we saw the cochlea, and we unrolled it and saw where those hair cells were sitting on the basilar membrane, and the little hairs on top had a tectorial membrane on top, and as the hair cells jiggled, it caused the hair to move and start an action potential. Right? We all remember that, right? Yes. Okay. So now we're going to get into just the last little bit of hearing and then jump into equilibrium. Okay. So the auditory ossicles. What were the three auditory ossicles? Stapes, malleus, and incus. Okay, if you want to remember them in order, the first letter is spelled mis. So M-I-S in order. Okay, so the auditory ossicles are going to jiggle with the information from the tympanic membrane, okay, from your eardrum, and it's going to concentrate that energy onto a smaller oval window, okay, which we'll get to on the next slide. The ossicles in the eardrum are protected by the tympanic reflex, so in response to loud noises, we're going to try to dampen the sound, which we're going to get to in just a second, but it's not effective for sudden loud noises. So this is going to be in play when something gets louder gradually, or if we're exposed to a loudness for a long period of time, we can use this tympanic reflex. Okay, so the tympanic reflex, we are going to tighten up some muscles around our ossicles. So I'm going to slide back a couple slides right here. So remember in this bottom picture, we have our tympanic membrane, we have our ossicles, and we have these two muscles, okay? The tensor tympani muscle and the trapezius muscle over here, okay? When those ossicles are vibrating, if something really loud comes to them, they're vibrating big vibrations, but they have muscles attached to them. If that muscle tightens up, the ossicle can't jiggle as much because the muscle is holding it tighter, okay? So it can take big noises and make them softer because the muscle is holding them tightly. Okay, that is your tympanic reflex. Okay. Oh, sorry, went too far. Okay, so that is what's happening. Okay, so our middle ear muscles are going to tighten up to prevent super loud noises from getting to your inner ear. Okay. This also happens before you speak to protect your ears from the volume of your own voice. So we've talked about a couple of times about how you sound differently when you're in a recording than you do normally. And part of that is because of the pathway of the sound. But then part of it is this too. So when you're talking, your ear muscles are tight, and so your ossicles aren't able to jiggle like normal. Okay? But then when you listen to a recording, those muscles aren't contracted, and you can hear what everybody else hears. Okay? So that's another reason why we sound funny when we listen to ourselves on recordings. Okay, so those hair cells. So our auditory ossicles are going to vibrate against the oval window, okay? And that oval window leads into the inner ear. What is the fluid inside that inner ear called? Endolip. Okay? So it's endolip inside that inner ear. Sorry. Okay? So when that oval window starts jiggling, it starts waves going in the endolip. And those waves travel through the cochlea and travel through the semicircular canal. Okay? So endolip in the cochlear duct vibrates, which causes the hair cell stereocilia to move against the tectorial membrane. And that's where just the hair cells are sitting there, tectorial membranes on top of the hair cells. And when they jiggle, the hair cells bend because the hair cells are held at the top by the tectorial membrane. Okay? The bending of that stereocilia will cause depolarization of the hair cell. Bending in the opposite direction causes the channel to close, which will give you hyperpolarization. So as that cell is jiggling and the hairs are being moved back and forth, the cell is depolarizing, hyperpolarizing as the wave comes through. Okay? When the hair cell is depolarized, it's going to release a neurotransmitter. And that neurotransmitter will start action potential on your cochlear nerve that comes out of your cochlea and goes up to your brain. Okay, so let's look at a picture of this on this next slide. Okay, so here again is our part of our ear that's picking up hearing. What's this organ called? Corti, or corti, however you want to say it, right? Okay, so the organ of corti, basilar membrane, your hair cells, the little hairs, and the tectorial membrane. So as the endolip going through this chamber has waves coming through, it's going to cause these cells to, the hair cells to jiggle, but the hair is held in that tectorial membrane. Okay, so as the hair cell moves, the hair is bent. Okay? So when the hair is bent, it opens these mechanically gated potassium channels. So we've talked about light gated channels, and we've talked about voltage gated channels. These are mechanically gated channels. So we have to change their shape mechanically in order to cause them to open. So when the hair bends, the channel opens. You let positively charged potassium in, which will cause it to be depolarized. Okay? And when he's stimulated, he will release neurotransmitters, start an action potential. All right. We good? Any questions? Okay. So, now let's get into some more specifics. So we said we were going to look at two properties of sound. We said there were multiple properties of sound, but we were going to only look at two. We said we're going to look at pitch and loudness. Okay, what determines the pitch? Frequency, so how fast the wave is moving. A higher frequency is a higher pitch. Lower frequency is a lower pitch. And then loudness is determined by amplitude, how big the wave is. So loud versus soft, right? Okay, so now we're going to look at how those hair cells send both those pieces of information back to the brain, okay? Okay, so first, when we look at loud sounds, okay, loud sounds are going to produce vigorous vibrations. Whoosh, 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 big vibrations, okay? Of the organ of Corti, exciting a greater number of cells over a larger area. So more hair cells are activated, you're going to get more signals sent back to the brain. So more signals sent back to the brain is going to say, we are loud. Okay? The brain is going to interpret that higher frequency of action potentials as a loud sound. Okay? Whereas if there's just a little vibration, only a few hair cells will be activated, less action potential sent, and the brain knows, hey, that was a soft sound. Okay? So that is our first characteristic. Okay, so this is loudness. Okay, then, down here at the bottom, we are going to talk about pitch. Okay, I'm going to show you on this picture first, and then we'll get to the words. So if we take our cochlea, and we unwrap the snail shell, okay, so we're unrolling him. We end up with this long tube, okay? When sound waves come through, they're going to cause that basilar membrane to form a wave. Okay, so it says it causes a standing wave in the basilar membrane, okay? There are hair cells all along that basilar membrane, okay? If you have a low frequency sound, you're going to have these big waves, and they're going to activate hair cells that are closer to the distal end of that cochlea. So they're going to make it all the way down here before they're actually activating hair cells. Okay? If you have a higher pitch sounds, really small waves, they're able to activate hair cells that are more proximal, that are closer to the beginning of the cochlea. Okay? And anything in between will activate hair cells anywhere in between. Okay? The way this works is a little complex. A simplified version is it has to do with the stiffness of the stereocilia at the top. The higher frequency waves have more energy in them. So the stereocilia at this end are really, really stiff. And so it takes a lot of energy to get them to actually jiggle. So the only waves that cause this to jiggle are high frequency waves. Whereas when you get down to the end of the cochlea, we're just kind of, anything will make us excited. Anything will make them jiggle. And so those low frequency waves make it all the way down to the end before they're actually able to excite a hair cell. Okay? So, if the hair cells up here are excited, it's going to be a higher pitched noise. If the hair cells down here are excited, we're going to have a lower pitched noise. Okay? I have a video for you guys to watch. It's really cool. Are y'all ready? Are you excited? Okay. Okay, so there's our ear. We're a little sound wave we're traveling through. External acoustic mediators will hit that tympanic membrane. Ooh, where's the
Here we are
cochlea?
with a view of the cochlea. The cochlea
Gonna
now
unwrap
uncoils, and
them.
we look at the basilar membrane, and now see what happens when we play individual tones.
Pretty low pitch. It's going to go far, medium,
Now
high.
a chord. And finally, something really complex.
You ready? So a lot of low noises up at the end. Oh.
So I kid you not.
Isn't that cool? Okay, so in order for music to work, in order for us to hear all those different pitches, we're using hair cells that are all along that cochlea, and hair cells over here are active, hair cells over here are active, which sends information to your brain, and your brain is able to magically understand that and make it make sense. And again, remember, we talked about pitch, whether it's high or low, and we talked about loudness, whether it's loud or soft. We didn't talk about what makes that organ sound like an organ instead of a trumpet playing that music. Okay, so it's a lot going on. Isn't that cool? Cool. Okay. All right. Hearing imbalances. The part, forgot this. The part of the chapter that we all love, right? Okay. So there's two broad categories of deafness, depending on what's making you deaf. Okay. So the first category is conduction deafness. That means that there is a problem getting the sound waves into the cochlea. Okay, so we can't conduct the sound waves from outside to inside. Okay, this can be caused by earwax buildup. If there's too much earwax in that auditory canal, you're not going to get sound waves to your eardrum. Okay, a perforated eardrum. If your eardrum is broken, you can't jiggle. Most common causes, though, is otitis media, which is an ear infection there in your middle ear. So as fluid and pressure builds up in there, it prevents those ossicles from jiggling. And autosclerosis of the ossicles. So in autosclerosis, the bones in your middle ear fuse together and grow like these bony, extra bony tissue. So if they're fused together and if there's extra bone there, they can't jiggle. And if they can't jiggle, you're not going to get the waves in the endolymph. If there's no waves in the endolymph, the hair cells aren't going to jiggle. No hair cells jiggling, no sound. Okay. So if the problem is autosclerosis, you can treat it surgically by removing the excess bony tissue there, and you can replace one or more of the ossicles or the oval window itself if it's grown closed. So that's problems getting the sound waves to the hair cells. Conduction deafness. We also have sensory neural deafness. So this is going to be because of some nervous system issue. Okay? And it's direct damage to neural structures. It can happen anywhere from those cochlear hair cells, that's the beginning of the nerve impulse, to the auditory cortical cells. So that auditory cortex that's in your brain. Okay. Presbycusis. Presby means old. So we're looking at deafness caused by old age. Okay, so it's the inability to hear your high-pitched sounds. It is often the first sensory neural deafness in old age. So when we unrolled that cochlea, and we looked at where the high-pitched sounds were and the low-pitched sounds were, where were the high-pitched sounds? At the beginning of the cochlea, right? So those are the ones you lose first. Okay, you lose them first. They're there at the beginning. It could be exposure to loud noises. So if something really loud's coming through, causing large vibrations, you're going to damage those hair cells. Okay, so don't listen to your music super loud. Okay. You also stiffen and tear the cilia, which can cause problems. Cochlear implants are a well-developed treatment for sensory neural deafness if there's something wrong with the pathway of getting things from your hair cells to the cochlear nerve. A cochlear transplant is a little microphone that will sit out here and then send the information to the cochlear nerve. Okay, so it takes the hair cells out of the equation. All right. So, with a buddy, see if you can answer these 5 questions. It covers both the eye and the ear. See what you can do. It means you have a good start studying. All right, you ready? Okay, number 1, the outer tunic is the B, tunica fibrosis. What are the 2 things that make up the tunica fibrosis? The sclera and the cornea. Okay, sclera is the white part, the cornea is the clear part in the front. Okay, number 2. Okay, this depends on how you read the question. So we're going to talk about it a couple different ways. So rods and cones are named based on, if you look at the name rod and you name cone, where did those 2 names come from? Their shape. Okay, so that's the answer to that. If we look at cones specifically, how are cones named? The type of light they're sensitive to. Okay, so red cones absorb red light, blue cones absorb blue light, green cones absorb green light. Okay, which could also be red, and their role in color vision could possibly be an answer to that too. Okay, but rods and cones themselves are based on their shape. Okay, number 3. Which of the following is used for hearing? Cochlea, good. 4, cloudiness is due to cataracts. And the 5, the bones that jiggle are ossicles. Very good. Okay, so if you got those, you should be well on your way for Monday. Okay, now we're moving on to your last special sense, to equilibrium. Okay, so equilibrium and balance. In humans, it's going to be divided into static equilibrium and dynamic equilibrium. Okay, and it's written over here, but the marker is really, we'll get to it on the next slide. Okay, so static equilibrium is going to be, that's not much better. Okay, static equilibrium is going to be horizontal movement, so horizontal movement, my brain knows where I am. Okay, is also vertical movement, so up and down, where I am in space. Okay, so it's responding to where gravity is. Okay, and then we also have dynamic or rotational equilibrium. So that's going to be picking up when I'm spinning in a circle. okay, and making you dizzy. So those are our two types of equilibrium. All right, so the first one we're going to look at is static equilibrium. There's a lot of words on the screen that are confusing. So here we go. So static equilibrium is going to be detected in your vestibules. Okay? Oops, wrong button. Okay, the vestibules are right here. Okay, so the vestibule is between the semicircular canals and the cochlea. The vestibule is made up of two large openings. Okay, the one is the saccule and the other one is the utricle. Okay, so this is the saccule, this is the utricle. Inside both of those is a sense organ. So the detector is going to be the maculae. The maculae is plural, macula is singular. So in our picture, this is a macula and this is a macula. Okay? So the maculae of the utricle and the saccule respond to changes in gravity and linear acceleration. Okay? And both of those are in the vestibule. Okay? So how this works, oh, let me read the rest of it. The utricle responds to horizontal movement. The saccule responds to vertical movement, up and down. Okay? And then the last bullet is the same as what was on the other slide. Changes in the sense of equilibrium in humans is divided into static and dynamic. Okay, so now let's look at this maculae. Okay, so in our macula, we have hair cells again. So cells with little cilia at the top. Sitting on top of the cilia is what's called an otolith membrane. Okay, so it's this liquidy stuff that sits on top of the hair cells, and it's full of these little otoliths, which are little calcium bone little chunks. Okay, so as you move around, it's like you're carrying a bowl of water in your head, and as you carry that bowl of water around, what does the water do? It sloshes and moves around. Okay, that's what this otolith membrane is doing. It's sloshing and moving around on top of those hair cells. And as it sloshes this way, it bends the hair cells that way. And as it sloshes back this way, it bends the hair cells back the other direction. Okay? So as you move, the otolith membrane moves around and depolarizes the hair cells. So that your brain always knows where your head is in relation to gravity. Pretty cool, right? Okay. That one is static equilibrium. And then dynamic equilibrium. So what we have over here is static is with the macula. And the macula has an otolith membrane on top. Okay. Dynamic equilibrium takes place at the base of each of the semicircular canals. Okay? So at the base of the semicircular canals is an enlargement called an ampulla. Okay? So this is your ampulla, the enlargement at the bottom of the semicircular canals. Okay? As you rotate your head around, the endolymph within your semicircular canals also rotates and moves around. Okay? Inside of the ampulla is a mound of hair cells with supporting cells called the crista ampullaris. So these guys, these cells, are the crista ampullaris. And they are hair cells, so they have little cilia sticking out on top. On top of the crista ampullaris is a gelatinous mound, okay, called a cupula. Okay, and that gelatinous cupula, as you move your head around the endolymph, will cause it to shift this way, or cause it to shift this way, which will move the hairs, the stereocilia on the hair cells. We call this a fluid movement response because because the fluid is moving and causing a response, right? Okay. So the cristae, the crista ampularis, is going to respond to changes in velocity of rotary movements of the head. So it lets your brain know that you're rotating around, okay? And velocity changes, whether you're going faster or slower. Yeah. Yes. It's going to be one of our things that we'll talk about on the next slide, I believe. Okay. So, we're going to talk about last class about this, and it's not important. It's just a dumb thing. But one of the things that can happen with these semicircular canals of rotational equilibrium, as your head knows that you're rotating, it knows that it needs to move your eyes to keep up with the rotation. So if you spin somebody around really fast, like on a spinning chair, and you stop them and have them stare at you, their eyes will go like this. They'll flip back and forth. Because their head still thinks they're spinning around because the fluid in their inner ears is still spinning. It's really cool. It's called nystagmus, but not important. Okay. So equilibrium imbalances. If your equilibrium is off, it's going to cause dizziness, which is also known as vertigo. Okay, so a syndrome, Meniere's syndrome, is an elaborate disorder that has to do with the endolymph that's inside the semicircular canals and inside the cochlea. Okay, so it's going to affect both of those. Repeated attacks of vertigo or dizziness, nausea, vomiting, difficulty standing, all of those have to do with equilibrium, right? So if you have balance issues, nausea, vomiting, difficulty standing, those are all due to problems within your semicircular canals. Okay? Tinnitus or ringing in your ears is going to have to do with this problems in the cochlea, because that's where the hearing comes from. Okay? So when you have too much endolymph in there, you're going to distort the membranes of the labyrinth and cause there to be bending of the hair cells, maybe even when you're not moving, okay? Because that endolymph is just going to push it and move it out of the way. So it makes you think that you're moving when you're not moving. So that's the dizziness, okay? So treatment. If there are mild symptoms, you can give the person anti-motion drugs, which is going to usually dampen the vestibular nerve that comes off the semicircular canals. So dampen the impulses that are going to the brain, telling it that you're spinning around in circles. Okay. Moderate, you can try to reduce the endolymph that's inside their ears with some low salt diet and diuretics. Okay, so that'll decrease the fluid level in the ear. Okay, if none of that works and it's severe, you can go in and surgically drain the endolymph from the inner ear. Fun stuff, right? All right. Another equilibrium imbalance is motion sickness. It's a common equilibrium disorder. It's where your senses tell you two different things. So your inner ear is telling you you're spinning around, but maybe your eyes are saying I'm sitting still because everything else around you is also staying still. Like if you're in an airplane, nothing inside the cabin of the airplane is moving, so your eyes are telling your brain you're still, but your ears and your semicircular canals are telling you a different thing, right? Because you're really moving. Okay? So, symptoms, pallor or paleness, rapid deep breathing, profuse sweating, nausea, vomiting. So, you can give them some over-the-counter drugs that will also depress those vestibular inputs. So, dampen the information coming from your vestibular nerve. Yeah? So, I have to know, like, what specific type of bracelet they are. Yeah, so there's some that are pressure point based, and there's not as much science behind the pressure point based methods of treating motion sickness as there are like chemically based. So this is a chemical base. We can give them something that's going to depress their vestibular input. We know that that's going to treat motion sickness. But there are also other places in the body where you can push on them, like an acupuncture type thing, that may have some effect. information for your test. I believe you have all that. I forgot to check before class to see if those figure numbers match the new book or the old book. Okay, so yeah, okay. But they should match what you got in your objectives. The pictures you need to know. You need to know your ear, okay, because you had that on your quiz. You need to know your ear, your cochlea, and you need to know your eye, that cross section of the eye. Okay, if you know those, you should be good. All right, so we are now going to start chapter 16. That's all your information for your test. So it's the autonomic nervous system with the sympathetic, parasympathetic, and then your special senses. So are y'all all ready? You know what you're going to do? You're going to study and you're going to do great? Yes. Okay. So before I pull up your PowerPoint for chapter 16, on Brightspace, you will see this endocrine table of hormones that is in the chapter 16 folder where you find your objectives in your PowerPoint. I put it up here this morning. It is a list of all the hormones you need to know for this chapter. It also has on here the target organ, what it binds to, and the action, what it causes. This is already filled out for you. You don't have to fill it out. But you do need to know all of these. So, the test is only 50 questions, right? It's only this chapter. We're giving you a big chart of hormones and what they do. A lot of your test is going to be matching. Right? Right. Okay. So, that brings us to, oops. Okay, dokie. So, as we talk about the endocrine system, we're going to be talking about a whole lot of hormones and what they do. So, we need to know what a hormone is. So, a hormone is something that is secreted by one endocrine gland or cell. It goes into the bloodstream, and then it's targeted towards cells in another organ. Okay? So, we're releasing it from one thing, it has to bind to something else. Okay, so the endocrine system as a whole is a collection of both the endocrine glands as well as extra hormone secreting cells that live within other organs. Okay? So there are glands in your stomach that are considered endocrine because they release things. Okay? So your stomach is not an endocrine gland, but he has endocrine cells within it. Okay. So the nervous and endocrine systems work together to help maintain homeostasis, but one is fast and one is slow. Which one is the endocrine system? Slow, right. So if we look at our picture of nervous system versus endocrine system, the nerve impulse, we have one cell, it sends information down. We have a neurotransmitter that is released right there at our target organ. It goes through the little synapse, binds to a receptor, and it causes a change. That neurotransmitter only lasts for a certain period of time, and then it's broken back down, sent back to the axon. Okay, so really fast, really quick response, but then it's gone. Hormones, however, are released by these little endocrine glands. It goes into the blood supply. That blood carries the hormone all over your body. That hormone then has to find the cells that have the receptor for him in order to bind to him and cause the response. So there's going to be lots of extra hormone floating around. It goes all over the body. He is not targeted just to that organ. Okay? So this hormone that's released doesn't go directly to the liver that he needs to bind to. He has to go everywhere and try to find the liver. Okay? Yeah. What do you mean? Okay. So, hormones have different jobs. Some hormones are stronger than others in that they cause a bigger response with what they bind to, and it takes a little bit of hormone to make a big change. Other hormones, they cause a little change, so you have to have a lot of them to cause a big change. If that's kind of what you're getting at, okay, yeah. Because there's tons of different hormones that do tons of different things. Okay, so the components of a hormone pathway. These parts are going to be similar to things that we've talked about before. So like the homeostasis pathway, the reflex arc, things like that. You know these parts. Okay, we're just going to put them with the endocrine system this time instead. Okay, so let me give you an example, and then we'll try to label the parts. Okay, so a well-known hormone is insulin. Okay, insulin is produced by your pancreas. Does anybody know why the pancreas secretes insulin? What's going on in your body that causes you to produce insulin? You got a bunch of glucose in your blood. Okay, so your blood sugar is high. High blood sugar causes the pancreas to produce. Oh my gosh! It's a golden doodle. I love your dog. It's kind of scary. That has to be a first. Okay. Put that down on my list. First time, 13 years of teaching, a dog was in my classroom. Okay. We're just going to start back at the beginning, before the dog came, okay? So, your pancreas produces insulin. Okay? He produces insulin in response to high blood sugar. So you've eaten something that's sugary. Your pancreas says, uh-oh, need to produce some insulin. Okay? The insulin goes and binds to the liver. Okay? It binds to other cells as well, but we're just going to focus on the liver to make it simple here. But it binds to the liver, and that liver says, uh-oh, there's too much sugar. I need to store that sugar away so I can use it later. So it sucks up blood sugar and stores it away as glycogen. Okay? And so when that happens, it lowers the blood sugar, and we go back to normal. Okay? There's another pathway that we can talk about that happens when your blood sugar is too low that causes the liver to release that sugar that he stored up. But we won't worry about that right now. We'll talk about it later. Okay, so in that example, what was the stimulus? What caused the hormone to be released? The sugar, the high blood sugar. Okay? Now, this second one we didn't talk about specifically. Okay, but what do you think realized that there was too much sugar? The pancreas. Yeah, so there's certain cells within the pancreas that's going to say, hey, there's too much sugar here, I need to change it. Now, in this instance, it's the own endocrine gland that is making that decision. In other examples, maybe the brain detects it and then sends a signal to that endocrine gland to then release the hormone. Okay? So in this instance, it is still the pancreas. Okay? What is the endocrine gland? What released the hormone? It's also the pancreas. Okay? The hormone. What's the hormone that he is producing? Insulin, right. Okay? And that goes into the bloodstream. And it's carried to your target organ that has a target organ receptor. What's the target organ? What's insulin binding to? The liver. Okay? And so there's a receptor on the liver that's going to bind to it. And the response, what's that liver going to do? Lower blood glucose level. So it's going to suck up glucose. Okay? We'll put lower blood glucose. Okay? So that is one example. Make sure you know those parts and can label a diagram. Okay? Right? But similar to the steps of things that we've talked about already this semester. Yeah. So there's the two types of diabetes. If one, you aren't producing enough insulin, there's other also forms where there's receptor issues for what the insulin is going to bind to. So if you're a type 1 diabetic and you're not producing enough insulin, you give them insulin shots. All right, mechanisms of hormone action. How does a hormone do its job? So first of all, hormones are going to bind to receptors on the outside surface of the target cells. And then they're going to cause a change inside. So it's going to trigger an intracellular cascade of events. Now, most hormones work this way. Okay, so they're going to bind to a and they're going to cause some kind of change inside. This is the same pathway as two of our senses use. So it's the G protein coupled receptor. Okay, the receptor is bound to a G protein. It activates him. That G protein goes and activates adenylate cyclase. Adenylate cyclase changes ATP to cyclic AMP, and then that cyclic AMP is going to go on and do its job. What were the two senses that use the G protein coupled receptor? Smell and taste. Your two chemical senses. Okay? Okay, so that's the way most hormones work too. They're binding to a receptor and causing a change. Now, the exception to this are steroid hormones. Do you guys remember from the beginning of the semester what class of organic compounds steroids are? Are they carbs, lipids, proteins, or nucleic acids? Lipids. Okay, I about said it at the beginning. Do y'all remember what category lipids are? Okay, so they're lipids. Okay. What do you know about the plasma membrane of a cell? It's made of lipids. So, phospholipids, exactly. So, if you are a lipid, you can make it through the phospholipid bilayer. You don't have to bind to a receptor on the surface. So, steroid hormones are going to go through the membrane and bind to a receptor inside of the cell. Okay? But then they can go to the nucleus and change genes that are making proteins. So they can turn genes on and turn genes off. Okay? So whatever the hormone is binding to, it will cause a cascade of events that will eventually result in the desired response. So when insulin binds to the liver, he's eventually going to do things that will cause that liver to pick up insulin. So it will send more insulin receptors to the surface, which will then pick up glucose. It'll send more glucose receptors to the surface, which will bind some more sugar, get it inside the cell, and then turn on the process of changing that glucose into glycogen. Okay? So those would be these downstream events that happen after the hormone binds to its receptor. Okay. There are 3 ways to stimulate endocrine glands. The first way is a humoral stimulus. So if you guys think back to the old days when they didn't know much about medicine, it was all about the 4 humors: your blood, your yellow bile, your black bile, and your phlegm. You guys remember that back in the day? Okay, and so it was all about having those balanced. So like if your blood was out of balance, they would bleed you, and then you would all be fine, right? Okay, so you can think about that to help you remember this humoral response. So a humoral response is what happens when that endocrine gland senses what's going on around himself and decides himself he's going to cause a change. He's going to release a hormone. So we are going to evaluate the blood that's coming to us and say, hey, do we have enough of what we need there, or do I need to release the hormone? So in this example, we've got our parathyroid glands. They look for the calcium level in the blood. So they monitor that. When they see that calcium levels are low, they release parathyroid hormone, which will go and cause the bones to release calcium and increase blood calcium level. Okay? But he himself is monitoring the humors. He's monitoring the blood. He's monitoring the yellow bile and black bile, whatever those happen to be. He's monitoring the phlegm and deciding what to do. Okay. Neural stimulus. What do you think he's going to be? Who tells him what to do? The nervous system. So a hormone is going to be released based on neural input. The nervous system tells him you must release a hormone, and he does it. Okay? So our example, we have stimulation of the adrenal medulla. What part of the nervous system stimulates the adrenal medulla? Sympathetic nervous system. And it causes that adrenal medulla to release norepinephrine, epinephrine, right? On your test on Monday. Make sure you know. Okay. So that's neural stimulus. And then we also have hormonal stimulus, which is kind of like hormone inception. Okay? So hormonal stimulus, a hormone has caused that endocrine gland to release another hormone. Okay, an example here. And if you can make these long chains, okay? So the hypothalamus is going to release hormones that go and target the anterior pituitary, which causes the anterior pituitary to release hormones, which goes to the thyroid gland, which causes the thyroid gland to release hormones. Okay? So it's a long pathway of one hormone causing another hormone causing another hormone. Okay? Alrighty. So now let's get into some anatomy of our endocrine glands. There aren't many figures in this chapter. This is one you need to know, your endocrine glands. Okay? But they're pretty easy. Up here at the head, you already know these guys. The pineal gland is in the back of the brain. The hypothalamus, you know where he is. You know where the pituitary gland is. He hangs off the infundibulum underneath the hypothalamus. Okay, the thyroid gland is around your neck. Your parathyroid glands are the little dots on the back. Your thymus sits on top of your heart. Your adrenal glands sit on top of your kidneys. Your pancreas is right in this region too. And then this is like a creepy picture because obviously this is a guy, but they wanted to show both reproductive systems. So you see both a testis and an ovary on this person. Okay, so there they are. It can happen. We're just going to keep going. Okay, so we're going to start at the top and work our way down. So we're starting with the hypothalamus. Okay? So the hypothalamus, you guys remember, is part of the diencephalon. It's in the center of the brain, and it regulates the body's primitive functions. Guys, remember, the hypothalamus is part of the control center for the autonomic nervous system, right? So he controls the autonomic nervous system, right? You guys remember that? Great test on that day? Yeah, good. Okay. So he regulates that background information, things that you're not thinking about, the automatic stuff. Okay, and then the pituitary gland, he's protected by the sella turcica. So remember, he is, if you take off the top of your skull and look in there, he's got little bone markings, the little Turkish saddle that the little pituitary gland sits on. And he's attached to the hypothalamus by an infundibulum, the little stalk. And the pituitary himself is composed of two portions, the anterior pituitary and the posterior pituitary. Okay. The anterior pituitary, the front part, is this part right here. He's also called the adenohypophysis. What do you see all over his surface? Veins. Okay? So there's a capillary bed right there on top of him. Why does he need a capillary bed right there on top of him? What's he producing? He's an endocrine gland. He produces hormones. Where do hormones go? The bloodstream, right? So we need lots of blood vessels there to pick up those hormones and carry them throughout the body. Okay, so there are 6 hormones. These are also on your chart. It's already filled out for you on Brightspace, okay? So the first one is FSH, or follicle stimulating hormone. In girls, it stimulates follicle development and egg development, okay? So a follicle is where the egg's going to grow. And in boys also have follicle stimulating hormone. It's important for sperm production, okay? Luteinizing hormone, or LH. It stimulates female ovulation and growth of the corpus luteum. Okay, so the corpus luteum is what's left behind after the egg is released during ovulation. Okay, in males, you also have luteinizing hormone, but you don't ovulate, right? So, in boys, it's called ICSH, and it stimulates the testes to secrete testosterone. So you'll see a lot of these hormones as we go through are named for what they do in girls, but not what they do in boys. And that has to do with them discovering the process of making babies, okay? Because we're more complicated, right? So they spend a lot of time looking at the hormones of girls, and that's where they get their names. All right. Number 3, thyroid stimulating hormone, or TSH. He stimulates the thyroid, okay, to produce his hormones. Adrenocorticotropic hormone, or ACTH, stimulates the adrenal cortex to secrete his hormones, as well as doing fat catabolism in adipose tissue. So adipose tissue is your store of lipids. Fat catabolism is breaking down those lipids and using them for energy. And he can also cause insulin secretion from the pancreas. Okay, so that's indirect control. Okay, number 5 is prolactin. So pro, increase, lactin, lactation. So it acts on the female mammary gland to promote milk synthesis in males. It does not promote milk synthesis. It enhances the secretion of testosterone. It's a good thing. Okay, and number 6, growth hormone. All of these that we've talked about before have pretty specific target organs. Okay, so if we're looking at prolactin, he binds to mammary glands. That's what he does. Growth hormone, though, there are receptors for growth hormone on all cells. Okay, because growth hormone causes cells to grow. So it stimulates cellular growth, mitosis, and differentiation, promoting overall tissue and organ growth. Okay, guys, we still have a little bit of time. I want to get to this slide, just so that we're on track with the other class. Okay, the posterior lobe, the back part of the pituitary gland. Okay, he does not produce his own hormones. The posterior lobe has hormones that are manufactured in the hypothalamus. So the hypothalamus sends it down to the posterior lobe to hold on to it. And then that posterior lobe will secrete it. Okay, our 2 hormones are ADH, antidiuretic hormone. It acts on the kidneys to increase their water retention, to keep you from being dehydrated. And oxytocin, OT, it stimulates uterine labor contractions and milk release by mammary glands. But again, boys also have oxytocin. Girls have more oxytocin too than just the uterine contractions. So oxytocin also in the brain, it's called the love hormone or the cuddle hormone. You might have heard it that way. But it's good for bonding. So uterine contractions happen during birth, so it helps the mama and baby bond together. But it's also released when you cuddle or around somebody you love. This hormone is released, which increases bonding because it gives you a good feeling when you're cuddling. Okay? So, oxytocin. Okay. Last slide, and we are caught up with the other group. Okay. So, pituitary secretion. So, all those hormones that we talked about are in the anterior and posterior pituitary. They are released only when the hypothalamus tells them to release it. Okay, so the hypothalamus is controlling these. The anterior pituitary, the hypothalamus is going to secrete both releasing hormones and inhibiting hormones to regulate the release of the anterior pituitary hormones. But the posterior pituitary is controlled by neuroendocrine reflexes. So there is nervous system control of the posterior pituitary. Okay, so hormones are released when signaled by nervous impulse from the